All right, welcome back. Hope you have had a nice break. Are there any questions? All right, so before the break, we introduced autocorrelation, and we also tell you how to access SPSS, okay? And this is the output from SPSS, okay? So now, why we need to do the calculation for autocorrelation? Remember this number we get, that is the R1, R2, etc. And we can also produce the graph from the output of SPSS, okay? And this graph, it is autocorrelation function. This ACF stands for autocorrelation function. This function tells us this is the lag time time lag time. See, this is lag time. We produce this graph. Okay. In this graph, you can say this is R1 equal to 0.572. Okay, and it becomes smaller, and then it becomes negative, From those autocorrelation, we can answer questions, commonly asked questions. What are the commonly asked questions about the data? So we can answer those questions. This graph, by the way, we call correlogram. This line here, it is upper confidence limit, lower confidence limit. So if the data is beyond this limit, that is significant. For example, R1 is significant because it is beyond this line. So why we need those autocorrelation coefficients? Because for time series data, we need to answer some questions. The fourth question, are data random? This is the question for time series data. So how do we know data are random or not? If the autocorrelation close to 0. So autocorrelation close to 0, we can say the data are random. And the other question we commonly ask is, does the data has a trend? Do the data have trend? How do we know if data have a trend or not? You take a look at of autocorrelation. If autocorrelation are different from 0, it is an indicator that data has a trend. If it is different from 0, it is also indicates the data are highly related. So we also ask question, are the data stationary? What is stationary data? Stationary data is the mean, is the data that the mean and the standard deviation changed around horizontal line. For example, if I give you data, some data like this might be a stationary because it is changed over the horizontal line. Okay, that is the stationary data. How do we know the data are stationary? If we can see the autocorrelation declined to 0, rapidly, we can say data are stationary. Last question we ask, are data seasonal? So the electricity consumption, gas consumption usually high during summer and winter. Those data tend to be a seasonal data. How do we know the data are seasonal or not? If the correlation coefficient, the significant occur at a seasonal time lag, that is a seasonal data. Okay, so significant occur at the seasonal time lag. Seasonal time lag, when it is a seasonal data, it is a 4. When it is monthly data, it is 12. Okay. So those are commonly asked questions for time series data. And we can use autocorrelation to answer those questions. Okay. Any questions? Why we do
silly one. How would you determine if it's seasonal or if it's cyclical, depending on, like, if it's kind of in line with the seasons? Can you say it's seasonal, or would it still be cyclical?
Yeah, that is a commonly asked question. How do you distinguish seasonal and cyclical? Okay, cyclical data. Cyclical data has the peak and the valleys. Okay, looks like the first graph. This looks like the cyclical data, typical cyclical data. It has the peak and the valley. And then how do you distinguish cyclical data with the seasonal data? Seasonal data tend to repeat itself at some point. For example, this year, January's data may be similar to next year's January data. And this year, April's data similar to next year, April's data. So it is seasonal. So we are learn, we'll use more techniques to explore that the differences between cyclical data and seasonal data later in chapter 5, when we do the data decomposition. We'll learn further. Okay. Thank you for your question. All right. Any other questions? So we talked about the autocorrelation formula, and there is also standard error. How do I calculate standard error of autocorrelation? This is the formula. Okay. You square all the autocorrelation, add them together times 2 plus 1, divide sample size, take square root. Okay. This is the formula. And why we need this standard error? Because we want to estimate the confidence interval estimate. When you estimate the confidence, using the confidence interval estimate, you need this standard error. Okay. So this is this formula. Sometimes, although individual autocorrelation are not significant, but as a group, the autocorrelation may be significant. That comes up with a new concept, LBQ statistic. It examines a consecutive autocorrelation as a group. Okay. N represents sample size in this formula. K is the time lag. M is the number of time lags to be tested. For example, when K equal to 10, maybe we'll go specific example later. Now just explain the formula. And RK is the sample autocorrelation function of the residues lagged K time periods. Okay. All right, so this is to examine a set of consecutive RK as a group. So next, let's take a look at some examples. This is example 3.4. It is about operating revenues for sales. Data taken is from 1955 to 2004. So in this example, we are going to explore if data has the trend. I have this data in SPSS, also Excel. This is the sales data here. Looks like no, this is sales. It is different. This is different data. Do I have that one? No, I may not have that data. This is this one. VCR, table sales. Yes, I do have this data. All right. All right, so let's look at this data here. This is example 3-4 in the textbook. We try to answer the question, do the data have a trend? Do the data have a trend? So first, let's take a scatter plot. Take a scatter plot to look at the data. This is original data. Okay, 3,307. Okay, so what you do, you can use Excel to do some basic analysis. So you can select column A and column B. And then insert. Choose the first one here. Scan, okay, timeline. Click OK button. And you get the sales, the data over time on x-axis. You have this is the year from 1955, okay, to 2003, 2004. And over y-axis, you got the original data here, y-axis. So looks like data from 1955 increase, and about year 1990, it is decrease. Okay, 1995 up again, and then 1990 to 2000 going down. So it has a trend. It has a trend. And if you produce an autocorrelation function for this one actually revenue. Okay. Y represent revenue versus X represent year. And if I copy this data into SPSS to produce autocorrelation function, so I'm going to just copy the data without label. I can create variable in SPSS later. So select data, right click your mouse, copy, and then go to SPSS, click File, New, File, New, and then select Control V. Okay, so you copied and paste data. Now you need to change the variable name. So instead of VAR 0001, this is maybe year or time. And this variable is the revenue. And I don't want decimals, so decimal is 0. So this is my data. You can adjust the width of the column. This is my data. Okay. So based on this data, you can produce autocorrelation function. Autocorrelation function. So you go to Analyze, Forecasting, Autocorrelation. So I want to copy this screen. So this is this one. Going to
Professor,
yes.
so I can't find on our course material where like this data is in Excel so that we could like do the same thing, copy and paste it. Do you know if you posted it to?
I haven't posted yet. I just entered the data by myself, by hand, based on textbook data. The reason is I asked the publisher, do they have the data? I asked 2 times, I still didn't get the response. I guess this textbook published maybe 2000 years ago, more than 10 years ago. I even asked the author of the textbook to see if I can get the data in Excel format. The author replied me back, but he is on vacation. The data is at his home. So I have to manually enter the data into Excel. So I will post the Excel file after this class.
Perfect. Thank you for
Okay.
clarifying.
Yeah, thank you for asking. So go back to my data. No, this is not SPSS. Not here. This is I did. Did I copy? No, chapter 3. Okay, I'm here. Okay. Okay. Forecasting and then autocorrelation. So the variable is actually revenue, is our original data. Okay. And if I click options, it is asked me maximum number of legs. If you check the textbook, it is 10. So you select 10. Time leg is 10. It could be any number, but we are interested in maybe just like 10 is enough. Okay. So you change that parameter to 10. So after that, you continue. And then click OK button. So this is your output. Let me double check the number with the textbook answer, ACT. Yeah, exactly the same answer, okay? This is autocorrelation. If you copy this, you will find it is the same answer as our textbook here. No, the data format is not the same. Maybe I'd better choose to copy the screen. This is another one. Okay. It's from here. Okay. So this is a autocorrelation here. Autocorrelation this table. I just try to copy screen so that I can have notes. And once you have this data, so what? So let's analyze this data. This is R1, R2, R3, etc. Those numbers are very big. Those numbers are significant because they are far away from zero. That's an indicator the data has the trend. If autocorrelation is significant, it has the trend. That is from the number. If you take a look at of ACF, autocorrelation function, okay, this diagram, you have the upper limit is this line, lower limit instead here. All these numbers, this is R1, R2, R3, are bigger than low upper limit. Okay, they are significant. They are significant means they are far away from zero. Okay, so that is from the graph or from the number, it tells us the data has trend. And when the data has the trend, so what? So what is the next step? Next step, you want to eliminate this trend by doing the difference. By doing the difference. Okay. So how do you do the produce the difference? It is this data, I think. Produce the difference. Okay, I'm going to do this data here, the same data set here. So remember this revenue is also the data for YT. Maybe I will change the variable name. Instead of revenue, I will say it is YT. Okay. The reason is I want to produce another variable, YT minus 1. Remember, how do we produce like 1 time like 1? How do we produce like 1 data? Like the 1 period. So you copy this data here up to here, copy, and then just move 1 level, down 1 item, paste. Okay, so you produced like 1. Okay. And this like 1, I will call YT minus 1. Okay. But the convention for the variable name does not allow me to use T minus 1. So I'm just going to use YT. It don't allow me to use minus because it is special simple. What do I do? Okay, maybe just T1 represent like the 1. Okay, like the 1. And then you do the difference between those 2 numbers. There is no calculation for first number, just for this number. Okay, you do the difference. So the difference. In Excel, it is easy calculation. You just do this minus this, but Excel, you can't. You cannot do that. You have to do this. Transform, compute variable. The variable name may be difference. What do I do difference? I use yt minus yt minus 1. So yt minus yt1. Okay, just do the difference. Click OK button. And then go back to original data. Out here, because I have too many data opened. Yeah, see, this is the difference. Okay, so I'm going to save this data before I lost it. Quick file, save as. This is data. So this data is yes. I already have this example 3.4. Example 3.4. All right, so I have that difference. Once I have that difference, now I can produce a scatter plot. Maybe Excel is easier. Did I have this time? Yeah, this is. So this one, I already have the difference. See, Excel, you just use this number minus this number, okay? And then you produce the line, okay? So insert, so select this number, press and hold down Control, allow you to select non-adjacent number. And then insert line chart. You see, this time the data is more stable because it is changed around the horizontal line. It is not like this data. You see the difference. Okay, I'm going to. You see the difference of these two graphs. After I do difference, the data change looks like around this horizontal line. And here you have trend. By doing the difference, I effectively eliminate the trend. Okay. So that is the revenue data. This is from sales. Okay. Any questions?
Professor,
Yeah.
so which means that like when we calculate the difference between RT minus 1 and the YT, there will be a better forecasting technique for this case. Is that correct? Just because it's more stable.
Exactly. Yeah, the original data is have the slope, looks like have the trend. After you do the difference, the data is more stable around this line.
Mm-hmm.
Okay, you eliminate the trend. Sometimes this is different. Sometimes people do the logarithm, take a log of original data, take a log of original data to eliminate the data patterns to produce more stable data. Okay, for this example, we just did the difference.
Okay, thank you.
You're welcome. Any other questions? All right. So once you produce this difference, so now we go SPSS. So we have difference. Now if you do the forecast, you do analyze, forecasting, autocorrelation. This time you want to use difference as the variable, okay? And you want to do 10. number of legs, you want to do 10, that's fine. And you click OK button to see what happened. So go to the output, is here. You see, when you do the difference, this is partial, but here, when you do the difference, this ACF stands for autocorrelation function. Most of them are within the limit, upper limit and lower limit. It is not like when you didn't do the difference, you see those correlation above upper limit and lower limit. Okay, so this one effectively, so this is more stable data here. Okay. I just want to maybe copy this. To my notes. So those are the techniques to analyze and explore data. Imagine you are throwing at this data. If you just have the numbers here. So this is the original data from the textbook. Imagine you just have this data in front of you. What can you do? You need to do preliminary work. The first thing, use Excel to explore the data patterns. Use Excel, the very simple tool. And next, you can use SPSS to get the autocorrelation. Okay. So that is in chapter 3, we just explore the data patterns. Okay, we haven't involved in the specific forecasting. That is actually in chapter 4, specific forecasting. Any questions? Okay, so I explained this one. Okay, we can produce this graph. And this one we also go over. Okay. This is after you do the difference. Okay. Sometimes after you do difference, it still has the trend. You do difference again. That is the second order difference. This is just the first order difference. Okay. So this is the autocorrelation function for difference revenue. We did this in SPSS. SPSS. So any questions? All right, and this table shows different methods or the techniques for forecasting. What are the techniques for forecasting? Okay, you can use the naive model. Okay, the naive model suitable for data. Okay, ST stands for stationary data. So naive model, stationary data. Okay, it can also apply the data with the trend or seasonal data. Okay. So we haven't dealing with naive model yet. This is just a concept. Okay, and the next chapter we are going to do simple average, moving average, exponential smoothing, etc., etc. Okay, those methods actually suitable stationary data. Stationary data. Okay, and for linear exponential smoothing, it is suitable if you have data has the trend. You can use linear exponential smoothing, etc. Okay. The most famous method is actually box jacking, ARIMA. Because this can apply all sorts of data, can apply for stationary, trend, cyclical, and seasonal. So apply for all the data. Any questions? Toward the end of chapter 3, how do we know which forecasting method is better? You use some criteria. One criteria is mean absolute deviation. So what this method does is you use original data minus predicted data, YT hat. You take absolute value, and then you add them all. After that, you divide it by n. That is MAD, okay, mean absolute deviation. We hope this number, the smaller, the better. Then you have the mean square error. Use original number minus predicted number squared. Add them all and divide it by n, etc. Okay, so those are the criteria for error. We hope the smaller the error, the better the forecasting technique. Okay. Any questions? I will explain other formulas when we do the problems. Okay, just look at the formula is meaningless. You have to know how to apply this formula in specific questions. All right, so now let's go over some questions. First, if I can. Question 1, explain the difference between qualitative and quantitative forecasting techniques. What is the difference between qualitative and quantitative? Any ideas?
Qualitative uses judgment.
Perfect. That is the important keyword. Quantitative is judgment or in opinion, okay, or take experts' opinion. And how about quantitative? It is about analyze data, manipulation of the data. That is the difference. Qualitative is a management, judgment, or intuition. Quantitative is a manipulation of the data. So what is time series? It is the data that over time. This over time could be week, could be months, could be quarter, could be year. Okay, data over time. Question 3, describe each of the components in a time series. What are the components in a time series data? Anyone want to try?
It will include like time.
Excellent.
And also like the value at a specific time.
That the components. Yeah, you are correct. We have a time, we have a value at a specific time. But what are those values consist of? The value.
The R value. trend.
Did we see the trend, the data, those value has the trend, right?
Mhm.
So this trend could be go up, could be go down, right?
Yeah.
Yeah. And anything else? Do we see cycling curve? Sometimes the data series have wave-like functions around the trend, ups and down, the peaks and valley, cycling curve. Okay. And then we have seasonal data. Seasonal. Actually, one student asked the question, what is the difference between seasonal and the cycling curve? Maybe I want to explain here just a little bit. We'll discuss in detail in chapter 5 when we do the data decomposition. So the cyclical data is wave-like functions around the trend. It is wave-like. And the seasonal data is the pattern of change, repeat itself year after year, quarter after quarter, month after month, week after week. So seasonal data is a pattern of change, repeat itself. Cyclical is a wave-like functions around the trend. Okay. So we have those are the components: 1, trend; 2, cyclical; 3, seasonal. The last one actually irregular part. Irregular. Irregular means some part of time series remaining after other components have been removed. It is other factors, okay, other things in the data. It is whatever left. The data, when you remove trend, you remove cyclical, you remove seasonal, whatever left, that is the irregular. Question 4, what is autocorrelation? What is autocorrelation? Can somebody try?
The correlation of the time series with its lags.
Excellent. The correlation of time series data with its lags. These lags could be 1 lag period, 2 lag period, etc. Fantastic. A correlation between a time series data and its lags. Question 5. What does autocorrelation coefficient measure? What does an autocorrelation coefficient measure? Measure what? What does this measure? It is measured to extent one variable related to its lags. The bigger the value, the more related they are. Okay. Question 6, describe how correlograms are used to analyze correlations for various lags of a time series. How correlograms, remember what are those used to analyze correlations? So I'll give you one example of correlograms. This is correlograms, okay? This actually correlograms, how this analyze autocorrelations. If a number in this gram beyond the limit. Those are the limit, upper limit, lower limit. That number is significant. That means it is highly correlated. Okay, and if a number within this limit, it is not significant. Okay, we use this number, this correlation number to answer. I give you the notes to answer commonly asked questions. Okay. This part is important here. How do we know data has the trend? If those correlation, autocorrelation different from zero, they have a trend. And how do we know data is seasonal? If those autocorrelation occur at seasonal time lag, sometimes it is 4, sometimes it's 12. If it is monthly data, it is 12. If it is quarterly data, it is 4. Okay. So that is that question. So go back to question 7. Question 7. Indicate whether each of the following statements describe a stationary or non-stationary data. So we know a stationary data is a data changed stable around the horizontal line. Those are stationary. Non-stationary means data changed, has the trend, is non-stationary. Okay. Okay, question A, a series that has a trend. If data has a trend, it is stationary or non-stationary. Non-stationary. Okay. B, a series whose mean and variance remain constant over time. You like this, remain constant over time. It is a stationary. Question C, a series whose mean is changing over time. Mean is changing over time, non-stationary. D, series that contains no growth or decline. It is stationary, stable. Okay. Any questions? All right. So question 8. Descriptions are provided for several types of series. Random, stationary, trending, seasonal. Identify the type of series that each describes. A, the series has basic statistical properties, such as mean variance, that remain constant over time. Remain constant over time. So question A belong to random data or stationary data or trending data or seasonal data. Which one question A belong to?
Random and stationary?
I would say just choose stationary. Because we don't have much information if this data is random, we don't know. We just know it is constant over time. It could be random, it could not be random. Okay, good guess. Question B, the successive values of a time are not related to each other.
Random?
Excellent. This is random. Okay, the successive value of time not related to each other. Question C, higher relationship between each successive value of data. Belong to which one? Random, stationary, trend, or seasonal?
Trending.
Which one?
Trending.
Excellent, trending. They have close relationship. Okay, or non-stationary, but we don't have that non-stationary country. Okay. And so those are questions we have gone through. Any questions so far? Shall we take a second break? After break, I will again go over questions from textbook. Okay, so let's say come back at 8:35, 10 minutes break. Okay. Back at 8:35, we'll do more questions from textbook. Okay. So I'm going to stop recording. After we come back, I will press record button again to save some cyberspace more. Stop.